students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as radiation. Now last lecture we had seen what is a perfectly black body. Today we are going to see the spectrum of a black body radiation. Now, the radiations emitted from a black body at any temperature are called as black body radiations. Right? The radiations emitted by a black body at any temperature are called black body radiations. At that temperature. Now, black body radiations are electromagnetic waves just like your normal waves, and they follow the laws of electromagnetic waves. That means it is a mixture of waves of different wavelengths. The intensity and the quality of the radiation depends upon the temperature. When you have a body, when you have radiations coming out from a black body, the intensity and the quality of radiation depends upon the temperature. The energy distribution amongst various wavelength of a black body has been subjected to research for long, and it has been observed that at low temperature the wavelength of radiation emitted is far in the infrared region, and these radiations cannot be detected by naked eyes. So when you have radiations coming out from black body, they are radiations coming out by, they are very similar to radiations that come out from any body. These radiations are made up of waves which have different wavelengths. How much heat energy is distributed and what is the proportion of each wavelength depends upon the temperature, right? At low temperature, most of the energy is stored in low frequencies and it is stored in the infrared region. Now, if the temperature is increased to 1100 Kelvin, then the emitted radiations consist of wavelength corresponding to red region. So from infrared region they move to the red region, and therefore the object appears as red to the human eye. Now if the temperature is increased beyond 3000 Kelvin, then the emitted radiations contain enough number of shorter wavelength to appear white. Right? Thus, a careful investigation of the spectrum of the black body radiations reveal that it consists of continuous distribution of wavelength of infrared, visible and UV spectrum, right? So at low temperature the black body would not be visible. At temperature above 1100 degrees Kelvin it would appear red. At temperature above 3000 degree Kelvin it would appear white. Same black body, right? So the color that you would see on the black body would depend upon the temperature, right? Can you please write this down? Right. Black body radiations are electromagnetic waves Black body radiations are electromagnetic waves they are a mixture of waves of different wavelength. They are a mixture of waves of different wavelength the intensity and the quality of radiation, the intensity and quality of radiation depends on the temperature Now at low temperature, the wavelength of radiation at low temperature, the wavelength of radiations are in the infrared region. Infrared region. At temperature above 1100 Kelvin, the wavelengths correspond to red region. Wavelengths correspond to red region, and hence the body appears red. Infrared, where the wavelength is extremely small. Your TV remote works on light. Can you see that light? No. It is when the spectrum is so small that it is not visible to the human eye. Wavelength corresponds to red region, and hence the body appears red. Right, at high temperatures, at temperature about 3000 Kelvin, the emitted radiations contain enough short wavelengths and the object appears white. So these are the radiations of a black body. So at extreme low temperature, it is giving out certain light, but that light is in the infrared region, and hence you are not able to see it. At temperatures about 1100, it appears red. At temperatures about 3000 Kelvin, it appears white. Next, let's see Wheel's displacement law. Now, the quantity of heat energy that is radiated from a perfectly black body is not uniformly distributed, right? Over the entire wavelength. That means at a particular temperature, suppose if I consider the temperature say at 100 degree Kelvin or at 200 degree Kelvin. At 200 degree Kelvin, the black body will be emitting so many waves which are different wavelengths. But all those wavelengths will not carry equal amount of heat energy, right? There will be only a particular wavelength that will carry maximum amount of heat energy, right? The maximum amount for every particular temperature, the maximum amount of heat energy will be carried by a particular wavelength, and as the temperatures increase, the value of the wavelength and the maximum energy is the value of the wavelength carrying maximum energy is decreased, right? And this was proved by Wien, and this is called as Wien's displacement law, right? Wien's displacement law says that the wavelength that corresponds to the maximum energy of a black body is inversely proportional to the absolute temperature, right? So as the absolute temperature increases, the wavelength that carries maximum energy will go on decreasing. Fine, do we get this? Let's write this down, guys. The quantity of energy radiated by a black body is not uniformly distributed over all wavelengths. Is not uniformly distributed over all wavelengths. It is maximum for a particular wavelength, which is different for different temperature. It is max for a particular wavelength which is different for different temperatures. Now, as the temperature is increased, the value of the wavelength carrying maximum energy decreases. Right? So thus Wien's law states, or Wien's displacement law states that Wien's displacement law states that the wavelength corresponding to maximum energy of a black body is inversely proportional to absolute temperature. That means his law says that the wavelength is inversely proportional to absolute temperature T. Right, or I could therefore say that lambda L into T is equal to constant. Right? So the wavelength that will carry maximum energy will be less at higher temperature. That means you will have a wavelength of say 10 hypothetically speaking, a wavelength of 10 centimeters carrying maximum energy at say 500 degrees, and instead of that 500 degree Kelvin, and instead of that, if I reduce the temperature to 100 degree Kelvin, instead of 10 centimeter, that would be 40 centimeters. So as the temperature goes on increasing, the wavelength which will carry maximum energy will go on decreasing. Fine, do we get this thing here? Now here we have lambda m is directly proportional to T. Lambda m into T is constant, and the value of the constant was determined by a scientist called as Bloomer, and this value of this constant was found to be 0.2898 into 10 raised to minus 2 meter Kelvin. Next, what do we understand by emissive power? How much heat energy would be emitted per unit time, per unit surface area at a given temperature is called as emissive power of a body. If I have a body, how much energy, radiant energy, would be emitted per unit time, in unit time, and per unit area, that would be called as the emissive power. So if I have an area of 1 unit, and in 1 second the amount of heat energy, radiant energy that would be emitted would be called as the emissive power of a body. Right? If I have a body of area 1 unit, and in 1 unit of time, the amount of heat, radiant heat energy that would be emitted would be called as emissive power. Write this down. What is emissive power? The quantity of radiant energy emitted per unit time per unit surface area at a given temperature is called emissive power. Represented by capital E. Next, what do we understand by coefficient of emission? Simple. What is coefficient of emission? It is represented by small e. Coefficient of emission is the emissive power of a body to the emissive power of a black body. Someone was asking me this question, that sir, why are we studying about a black body when practically a black body is not present? We are studying about a black body because we need this here. Coefficient of emission is the amount of emission done by any body to the emission done by a perfectly black body. It is the ratio of the emissive power of a body to the emissive power of a perfectly black body. And I already explained to you what is emissive power. It is the amount of radiant energy emitted per unit time per unit area. This particular ratio of any body compared to that of black body is called as coefficient of emission. Fine, do we get this thing here? Can you write this down? Coefficient of emission of a body is defined as the ratio of radiant energy emitted per unit time per unit area at a given temperature to the same radiant energy emitted energy emitted per unit time per unit area by a perfectly black body. Per unit time per unit area, it's a ratio of radiant energy emitted per unit time per unit area at a given temperature by a body to the radiant energy emitted per unit time per unit area by a perfectly black body. One is by a body and the other is by a black body. So thus I could also say that coefficient of emission is the emissive power of a body. It's the ratio of the emissive power of the body to the emissive power of a black body. I could also say that this is ratio of emissive power of a body to the emissive power of a perfectly black body. Now suppose if I consider the emissive power and of a body and the emissive power of a perfectly black body for a particular wavelength, then that would be called as monochromatic emissivity. What is monochromatic emissivity? Here I am considering for all the wavelengths. Instead of considering this for all the wavelengths, if I consider this for a particular wavelength, then that would be called as monochromatic emissivity. Write this down. Monochromatic emissivity of a body is the fraction no, it comes under emissivity only. It's just a type of emissivity. Instead of taking all the wavelengths, I'm taking just a particular wavelength. So monochromatic emissivity of a fraction of radiation emitted. Monochromatic emissivity of a body is the fraction of radiation emitted by the body per unit area per unit time. Radiant energy emitted per unit area per unit time at a specific wavelength compared to that emitted by a perfectly black body compared to that a black body per unit area per unit time at the same temperature. Per unit area per unit time at that temperature. So the only difference is that in monochromatic emissivity you will check only for a particular wavelength. Right? Now if a body can emit heat energy, it can also absorb heat energy. So the quantity of radiant energy absorbed per unit area per unit time of a body at a particular temperature is called as the absorption power of that body. How we had emissive power, similarly we have absorptive power. Right? What do we understand by absorptive power? It is nothing but it is the quantity of radiant energy. Quantity of radiant energy instead of emitting, you are absorbing. The quantity of heat energy, radiant energy absorbed per unit area per unit time per unit area per unit time at a given temperature is called as its absorptive power. Now if you have absorptive power, you will also have coefficient of absorption coefficient of absorption is the ratio of heat energy absorbed per unit area per unit time of a body to the amount of heat energy absorbed by a perfectly black body. You are comparing the absorption power of a body to the absorption power of a perfectly black body. So coefficient of absorption is the ratio of the absorption power of a body to the ratio of absorption of a perfectly black body. You just write this down, people. Coefficient of absorption is the absorptive power is the ratio of absorptive power of a body to the absorptive power of a perfectly black body under similar conditions. So coefficient of absorption, that means therefore I can say this is another definition for coefficient of absorption. Right, same thing. Right. Next, what do we understand by, now that we've done black surfaces, let's move on to grey surfaces. What is a grey surface? right? Now a gray surface is defined as that surface whose emissivity is same for all wavelengths, right? Generally the emissive power by Wien's law we know is maximum for a particular wavelength. Instead of the emissivity being maximum for a particular wavelength, if it is same for all the wavelength, then that surface is called as a gray surface, right? A gray surface is defined as one whose emissivity is same for all wavelengths. Right? Now that we've done the basic definition, we'll do the theorems in the next lecture. We'll stop this here for the day. Thank you very much.